So let us consider the formation of N2 molecule. In N2 molecular energy level diagram is like boron B2, like C2 carbon. You try to find out the molecular energy level diagrams for C2 yourself. Let us try to work out for the nitrogen. In nitrogen, as you know, nitrogen electronic configuration is 1s2, 2s2, 2px1, y1, z1. Now, in the molecular orbitals, when two nitrogen atoms combine, in N2 the molecular orbitals are formed are like sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, which has same energy as pi 2py, which has lower energy than sigma 2pz. Then we have pi star 2px, which has same energy as pi star 2py, which has lower energy than sigma 2pz star. Now, total number of electrons nitrogen has is 7 plus 7, 14. These 14 electrons I distribute like sigma 1s2, then according to above principle, sigma star 1s2, 4 over, sigma 2s2, 6 are over, sigma star 2s2, 8 are over, pi 2p x1, y1, x2, y2. That is total how many are over? 2, 4, 6, 8, 10, 12. Sigma star 2pz. Now 14 electrons I have accommodated in this. Now the bond order in this case is equal to half into number of electrons in BMO2, 4, 6, 8, 10. 10 electrons are in bonding molecular orbitals minus anti-bonding molecular orbitals have 4. So the bond order in nitrogen is 3, and because there are no unpaired electrons, it is diamagnetic. Because bond order is so high as 3, N2 molecule is very stable, which is we are representing traditionally as N triple bond N. It is very, very stable. It is very difficult to break the N triple bond N. Roughly it requires 950 kilojoules of energy per mole. Therefore, N2 is very, very stable. Practically it behaves like an inert gas because of the difficulty in breaking the triple bond. If you want to look at the molecular orbital energy level diagram, it can be shown like boron. See, 1s are giving sigma 1s, sigma 1 star 1s. 2s are giving sigma 2s, sigma star 2s. And 2p xyz are combining to give pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma 2pz. For nitrogen, the 14 electrons are there like 1s2, 2s2. I can write 2px1, y1, z1, 1s2, 2s2, 2px1, y1, z1. 14 electrons, 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. So, if I am looking at nitrogen, the nitrogen has no unpaired electrons in the molecular orbitals which are located here, and nitrogen bond order, if you can count, as half into number of electrons in BMOs minus number of electrons in ABMOs. The bond order appears to be 3. That is what about nitrogen. However, when I am looking at oxygen, the molecular orbital energy level diagram changes. How it changes means this pi 2px, pi 2py will be of a little bit higher energy than sigma 2pz. This is the only change. The position of these two will come here from this place in nitrogen. From here, which are below 2pz in nitrogen, they go above 2pz in oxygen onwards. Therefore, if you want to write the electronic configuration of O2 according to molecular orbital theory, you can construct the MOED. Can you construct the MOED? If there is time, we try to do at the end of this. First, we write the molecular orbital energy level order and the bond order calculation. Oxygen electronic configuration is 1s2, 2s2, 2p, 4. Now, the O2 molecule has total how many electrons? Each oxygen has 8. O2 has total 16 electrons. Now, if you consider all the 16 electrons, you write sigma 1s2, then sigma star 1s2, sigma 2s2, then sigma star 2s2, then sigma 2pz2, then pi 2px, which has same energy as pi 2py. They will have how many? 2, 4, 6, 8, 10 are over. So I can happily place 4 more. And then pi star 2px, which has same energy as pi star 2py. Now both will have 1 electron. Because in degenerate orbitals I should not pair up unless each fellow gets 1 electron. It means there are 2 unpaired electrons in anti-bonding molecular orbitals of oxygen. It makes O2 paramagnetic due to 2 unpaired electrons. And also the bond order of oxygen, if you can work out, half into number of electrons in BMO2, 4, 6, 8, 10 minus number of electrons in ABMOs 2, 4, 6. Bond order works out to be 2. This is the story of oxygen molecule with respect to electronic configuration of molecular orbitals. If you want to draw the molecular orbital energy level diagram, let us try to accommodate that. This is AO's 1s, this is AO 1s of other oxygen. This is 2s, it is 2s, and then let us take some space. It is 2pxyz, 2pxyz of another oxygen. When I combine 1s, 1s, I get sigma 1s and sigma star 1s. Sigma 1s, sigma star 1s. No issue, right? Now, 2s can combine to give sigma 2s, and this is sigma star 2s. And now, when I am looking at this, x, let us take z, y, x, z, y, x. When z and z are combining, I am getting sigma 2pz, sigma star 2pz, and now the yx combine to give pi 2px is equal to pi 2py molecular orbitals. Similarly, pi star 2px is equal to pi star 2py. Now, this is the molecular orbitals energy level diagram. Now, for oxygen electron configuration 1s2, 2s2, 2p, you can write 4. Okay. For this also 1s2, 2s2, 4, 1, 2, 3, 4. Right. Total number of electrons oxygen has 16. I am writing 16, 1s2, 2s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x1, y1. Then remaining 2 I put pi star 2p y1, pi star 2p y1, x1, y1. Because it has 2 unpaired electrons in anti-bonding molecular orbitals, its nature is paramagnetic, and its bond order is half into number of electrons in BMOs 2, 4, 6, 8, 10 minus number of electrons in ABMOs 2, 4, 6. That is equal to 2. Now, it is of interest to see, this is all about oxygen. Now, if you consider O2